Welcome back to day 2. We have 2 talks this afternoon, separated by a tea break, and then we have a discussion session to end off today. Our first talk this afternoon is Branstator, and he's going to be talking about the fluctuation dissipation.
Thank you. I really appreciate having the opportunity to speak to you this afternoon about the fluctuation dissipation theorem, which is a theorem that has its roots in statistical physics. It was first formulated early in the 20th century, but it was not until about 1975 that it made its entry into climate science, when Chuck Leith proposed that the climate system might be a system whose properties were close enough to the properties of a dynamical system for which the theorem would be valid, that perhaps climate scientists should take advantage of this fact. But since then, this idea has been fairly dormant. There have been a couple of isolated instances where people have tried to use the theorem, but there's been very little work on this up until a few years ago. But now we're starting to see that it does seem to be a useful tool for certain applications. And today I wanted to tell you about an application that I'm making of the theorem. Now, I have a particular problem in mind, and I'm going to build on research that I've done in conjunction with Andre Gritzen and Andy Maida. And although I want to tell you about a particular application, I'm really going to use this application as a vehicle to try to convince you of the usefulness and power of this theorem. So here's how I'm going to go about it. First, I want to tell you about the physical problem that I'm interested in. Then I'm going to state the theorem and try to explain why I think it has a place in trying to understand this particular physical problem. Then I'm going to show you some tests. Of course, the theorem, the properties that a system needs to have for the theorem to be strictly valid are not exactly satisfied by how I'm going to apply it. I mean, it wouldn't be very interesting if it was exactly satisfied. And so I'm going to do some tests to see whether the theorem is still giving us useful information in spite of this fact. I'm going to show you some examples of how once one has constructed a response operator using this theorem, one then can do some really interesting kinds of analysis. And time permitting, then I'll actually get to the current application that I'm making of the theorem. Okay, so first let me tell you about the physical problem. And it has to do with this distribution of rainfall on the planet. And you can see that near the equator, there's this distinct maximum. And of course, this is largely what drives the general circulation. This is the vehicle by which the sun's energy a lot of it is injected into the atmosphere. But there's a lot of temporal variability in this rainfall. And this variability takes place on all time scales. And so you'd imagine that that variability has some consequence for the circulation of the atmosphere. The atmosphere will feel that variability. And it's important enough that one would like to know how the atmosphere responds to the variability in precipitation here near the equator. So this is a problem that has been thought about a lot by climate scientists, but for a very particular time scale, namely interannual variability. And the reason for that is this picture. This is showing the anomalous circulation in the upper troposphere that occurs during El Nino events. El Nino events are when SSTs here in the central and eastern equatorial Pacific are warmer than normal that leads to a rainfall anomaly, and this picture then is showing the anomalous circulation that occurs as the atmosphere reacts to that precipitation anomaly. And so you can see that this local event affects much of the globe. And so, of course, this is actually the biggest signal on interannual timescales, and so a lot of work has gone into trying to understand why this looks like this. But this is only one part of the problem, and that's because there is variability in equatorial precipitation on all time scales. And here's a diagram demonstrating another aspect of this. Here we're looking at one particular year 2000 for 1 month. This is looking at a segment between the western part of the Indian Ocean and the central Pacific. And this is showing OLR, which is a surrogate for convective precipitation. And you can see there's organization to the variability of precipitation. And the feature that is most prominent on this diagram is this eastward propagation of some kind of organized convection. Well, this is actually a phenomenon that has a name. This is the precipitation signature of what's known as the Madden-Julian oscillation, which is a mode of variability that occurs fairly prominently. And you can see it's taking a few weeks to travel across something like a third of the globe. Now, if we look at a similar picture of OLR, but plotted a little bit differently, we see that not only is there this kind of organized convection going on with this kind of evolution, but embedded in that are features that have very different propagation properties. You see many features propagating towards the west at faster rates than this envelope propagating towards the east. There are some features propagating towards the east at very fast rates. These correspond to various tropical phenomena. And so one would like to know how the global atmosphere responds to these kind of features, which are where the heating is a function of time. So this problem has not been studied very much, whereas the response to stationary heat sources has been studied quite a bit because of El Nino. This has not been studied very much, and so I'd like to find a way to do that. So to do that, let me tell you a little bit about the physics that's probably involved. And a lot of this is just based on what we have learned from the response, how the system responds to El Nino. So the most important thing is that planetary waves on this spinning planet are dispersive, so they have group velocities, and so that's the main mechanism by which something that's happening locally can influence remote regions. And so here's just a simple example of this, where I've taken the linearized barotropic vorticity equation, linearized it about solid body rotation, put a little blip of vorticity right here on the equator, and you can see after a few days that's starting to get pulled apart by the dispersion. By 7 days, you can see a distinct group velocity. Of course, the response to a source, like a steady source, is going to be a sum of pictures like this. So you can see we get this nice arch out of a steady solution in these simple dynamics, which just qualitatively corresponds to this kind of arch as the system reacts to the steady heat source. Okay, so one expects those same kind of dynamics to have something to do with a heat source, which is a function of time. And this very simple linear theory is giving you some suggestions as to how the response is going to be a function of the temporal characteristics. So here I've taken the same equation and now had my heat source move along the equator. Here it's moving towards the west. Here's the response to such a westward moving source. Here's the response to an eastward moving source. And you can see some qualitative differences that result because the source is moving differently. So I just want to point out three things. You see the scale of the response is somewhat different. As it moves towards the east, the scale gets compressed. That's just some Doppler kind of effect. You can see that the group velocity is weakened somewhat for this eastward moving source. And you can see the ray path is somewhat different with the westward source having a much stronger meridional component than the eastward moving source. So linear theory can give you some idea of the kind of sensitivity to the details of how the heating is moving with time. But this can only be a part of the story because we know that the processes are more complicated than this. So here's an example to suggest that things are more complicated. This is the response to a steady heat source in two different locations on the equator. You can see that the structure, again, we're looking at upper tropospheric stream function. Again, it's a steady response now. You can see the response is very sensitive to where you put the heat source. So the same kind of things that are influencing this will likely come into play when we're trying to understand how the system's reacting to a moving heat source. And there are a couple of reasons why the response turns out to be so different for these two locations. One has to do with the perturbation response is superimposed on a rather complicated background state with strong gradients which are influencing how the rays are being refracted. These gradients act as internal energy sources which are also affecting things. There's a second complication, and that is that this is actually a multi-scale problem. The large-scale reaction to a local heat source, which I'm again showing you another example of here, has an effect on faster time-scale variability in the system. Variability on synoptic timescales, that is the timescales involved with the storms that everyone's familiar with. That variability is concentrated in certain regions of the globe, these which are depicted in this diagram. These are referred to as the storm tracks. And this distribution is distorted when one distorts the large-scale planetary waves. But that actually has a feedback onto the low-frequency large scales, and that's what's shown in this diagram. Associated with these eddies are momentum fluxes, which in turn are rectified in such a way that they feed back onto the large scales. And you can see in this case, which again is a model simulation of how the system responds to a heat source in this location, the feedback as this large scale affects the faster time scale transients is a positive feedback. And this actually is a large part of what's helping to maintain this reaction. So these kind of effects, of course, are not going to be amenable to linear analysis. And so if we want to do some kind of systematic examination of how the system is reacting to a variety of heat sources, in particular ones that are moving, we have to be able to include these kind of effects. So we want to be able to do a systematic investigation on the one hand. On the other hand, we want to include all the relevant dynamics. So that's where fluctuation dissipation can come into play. So let me now briefly describe to you what the theorem says. The theorem says that if you have a dynamical system, a discretized dynamical system, and if you want to know about averages, ensemble averages, where you're averaging over the attractor with phi being the state variable and a being a functional of the state, then in order to see how the system, how these averages are going to change if one changes the forcing of the system, the fluctuation dissipation theorem tells you what the operator is, which when multiplied by this change in the forcing gives you the change in your ensemble average. Now we're going to do this for the limiting case of very weak forcing. By doing that, we can assume that this response operator is a linear function of the forcing. This does not mean that we are saying that the underlying dynamics are linear. We're just saying that we're restricting ourselves to a weak enough forcing that the response is going to be a linear function of that forcing. So for this kind of situation, it turns out that if we make two additional assumptions, one being that there's a stochastic term in our governing equations, that's primarily so that the PDFs of the system are well behaved. They don't have some odd fractal distribution. And second, that the accompanying Fokker-Planck equation has a unique solution. If we have these two properties, then one can find this response operator just by observing the intrinsic fluctuations of the system under equilibrium conditions. So this then is the expression for what this response operator looks like. And you can see that the only things contained in this expression are correlation statistics between the density function and the state variables. Sometimes at lags. So again, this says that one can generate this response operator without knowing the governing equations, without seeing how the system reacts to any particular external source. All you have to do is watch and collect some statistics of the structure of the intrinsic variability of the system. So that's the good news. The bad news is that this is a difficult expression to evaluate. Okay, we're looking at derivatives of the multidimensional PDF, something that would be very difficult to actually observe with any accuracy. But we can overcome this by assuming that this PDF is Gaussian. And if we do that, then our expression becomes much more tenable. Now all we need are lag correlation statistics between functions of state and the state itself. This is just the lag zero covariance matrix. Okay, and just to carry this a little further, in the simplest case where this functional is just the identity, so now we're just asking how mean state variables react to the external stimulus. Now the expression becomes very simple. Okay, now there's one one additional thing I wanted to tell you, and that is about the theorem itself, and that is I showed you the integral form of it, but there's an incremental form of this in which one asks how the system would react to a pulse forcing, a forcing that just lasts for an instant. And so, as you can imagine, that just can be derived from the integral form in a natural way. Once one has that, then one can find the response at some future time of a forcing which is a function of time. And of course, this is the situation we're interested in. So this is the application that I'm eventually going to make use of right here, or sometimes where this covariance involves a functional of state instead of just a state. Okay, so that's the fluctuation dissipation theorem as we're going to apply it to some problems. Now we've made a couple of assumptions that I want to justify. The first is that we've assumed that the PDF of our system is Gaussian. Of course, it's not exactly Gaussian. I'm going to apply this theorem actually to a general circulation model, not the data from nature, except maybe the very last slide if I had. Yes?
Why is it called fluctuation dissipation?
Well, that I don't want to spend much time on this, but it's for historical reasons. It goes back to the original application or where this was derived from. It actually, like Einstein worked on these kind of ideas, and there the germ of this idea came from Brownian motion, and so in that context, dissipation has to do with the energy that's lost, that has to be made up for as the system reacts to a forcing. So in some sense, dissipation is in this odd way, is a synonym for forcing. So there we're looking at a correspondence between fluctuations and the response to forcing. It's an odd twist that the language has taken, an unfortunate twist. Okay, so anyway, as I was saying, one of the assumptions we made was that the PDF is Gaussian, and if it's not exactly Gaussian, the application I'm going to make is for a particular general circulation model which Judith Berner and I have examined, and we've looked at its PDF. Here are some these are projections onto some of the dominant planes of variability in this model, and so you can see that there are some departures from Gaussianity, but this at least says that it's not completely unreasonable to make this Gaussian assumption. The second assumption that we had to make was that the forcings that we're interested in are weak enough that the response is going to be a linear function of forcing. Okay, so, well, here's my justification that the forcings of interest are that weak, and that is to go back to nature and the one problem where we know something about how the system reacts to such a heat source, and that's the El Nino case. I showed you this. There are events in nature of the opposite polarity when instead of warm SSTs, one has unusually cold SSTs, which leads to a deficit in rainfall, and here's how the system reacts to that. I think you can see that the two structures are pretty much the same. So it's plausible that the problems we're interested in are within this linear limit. Okay, now I'm going to apply this to a general circulation model. I'm going to see if I can reproduce the reaction that a general circulation model has to specific heat sources using the fluctuation dissipation theorem. That's going to be my test. This has a couple of advantages. One is I can actually do a test. I know what the right answer is. The GCM I can put any heat source I want with any kind of properties into the GCM, see how it reacts, and then compare those to the response that's predicted by the fluctuation dissipation theorem. Another advantage of this test bed is I'm able to integrate it for a very long time. Therefore, that enables me to calculate these lag correlation statistics that I need to high accuracy. And so I'm avoiding some practical problems that might arise if one wanted to apply this to some system where you did not have a very long data set. But for now, we're going to keep things to our advantage and use a very long general circulation model integration as the test bed. So even though I have this very long data set to work with, it still turns out that I need to reduce the dimensionality of the system. And so I'm not going to go into exactly how I've done this, but we found that we can ignore certain state variables because the system is more or less in balance. And in addition to that, we're using various EOF strategies to reduce the dimensionality. So we start out with a system that has 18,000 spatial degrees of freedom, and we reduce that by a factor of 10. So now we're ended up with a state vector that has 1,800 elements. That's what we're going to use. Okay, so let's try it out. So I tried to briefly make the case that the fundamental building block of how the system is going to react to an arbitrary source is how it reacts to a pulse. All responses to all sources can be thought of as being a combination of responses to various pulses. So the basic question is, can FDT match the GCM's response to a pulse forcing. So that's my first test. So here is how the GCM does respond to a heat source that's turned on in this location. These are necessarily ensemble average reactions. So this is the average reaction to an ensemble of 5,000 initial conditions, which are spread over the system's attractor. We integrate each of these forward in time 3 days with this heat source turned on, and then compare the average of that to the long-term average of the undisturbed system. So here's the anomalous response to this switched on heat source after 3 days. Then we turn off the heat source and continue the integrations. And so here's how the reaction continues to evolve. And so this is, for example, the reaction 10 days after this pulse. Okay, and so you can see this kind of dispersion that I showed you from the linear result. So can FDT reproduce this? Here's the corresponding solutions using response operators that came from just gathering lag correlation statistics from the undisturbed system. And so I think you can see that these operators are in fact doing a nice job of reproducing most of the features. It does have some trouble early on. You can see that, for example, it's producing this, which has not actually occurred yet. But for the most part, it's getting almost all of the evolution. So we see this as a success of FDT when applied to this complex general circulation model. Now let's do another test. Remember, I showed you how the system reacts very differently depending upon where one places a steady heat source. I showed you these two responses of this GCM to heat sources in 2 locations. If we ask FDT how it thinks the system's going to respond to these cases, here are the responses. So you can see that it's getting this high sensitivity to location very nicely. And then the third test I want to tell you about is one where instead of looking at how the mean state is responding to an external stimulus, we instead are looking at how functionals of state are reacting. This was a generalization to the theorem that's occurred since Chuck Leith originally introduced it. So here's the test. It's like the other tests I've shown you. We put a steady heat source in this location. Here's how the mean, how a mean state variable stream function at 300 millibars reacts in the general circulation model. Here's how the storm tracks react. This is how eddy variance for bandpass eddies is different when one puts the heat source here than it would be under undisturbed conditions. And so you see what's happened is that the storm track has shifted southward in reaction to the fact that we have enhanced westerlies here. Similarly, eddy fluxes associated with the bandpass eddies also react to this heat source, and that's what's shown here. So we're getting a convergence of westerly momentum here and divergence here, for example. All right, so now let's see how well the theorem can reproduce that result. And here are the corresponding responses just coming about from observing the intrinsic variability of the system. And of course, it's probably not a surprise, given earlier results that I showed you, that its estimate of how the system will react in terms of the mean state variable is a good reproduction of what actually happens. But now we can see for these functionals of state, these functionals telling us about dynamical properties of the system that we're interested in. It's also giving us pretty good estimates of that. All right. So those are our tests. Of course, we've done a much more extensive systematic testing. I'm just giving you some samples to show you how this works. All right. Now, the next thing I want to do is just show you some applications that a climate scientist would be interested in making once you have this response operator. There are various problems that can be addressed given this operator. The kind of problems that cannot, the thing is that where I come from, if a scientist is confronted with how is the system going to react to something, her or his way of addressing that is to take a general circulation model and see how it reacts, okay? But there are problems that cannot be addressed that way. Problems where you need to know the reaction to many external or an infinite number of external sources, like optimization problems, for example, okay, or inverse problems. These are the kind of things that cannot be done with a general circulation model, but once you have this operator, which I've shown you as a very accurate approximation to how the GCM would react, then you are in a position to answer some of these questions. So I'm going to show you a few examples. So first has to do with what I call control. So suppose one wants to know an efficient way to get a particular reaction to the system. And here's a kind of reaction that one might be interested in. This structure in this panel is showing you a prominent pattern of variability for this model and in fact for nature. This is the model's counterpart to what's known as the Arctic oscillation. Christian referred to this mode of variability in his talk. And you can see it actually has a big influence on what goes on in Europe. So let's use the operator to find out how one can stimulate this pattern. And one way to do that is to construct something like a Green's function. So what we've done is using the response operator that gives us response of the mean state, we've put a local heat source at each location on the globe, use the operator to find the system response to that, then projected that response onto this pattern of interest. And here I've plotted the projection. So like I said, this is like a Green's function. So it's telling you that if you want to change the amplitude of the Arctic oscillation, the best way to do it is to put a heat source here south of India, or perhaps here to the northeast of Australia. Or alternatively, put a negative heat source here near the Arctic. And these turn out to be actually good estimates of good places. This is what FDT is referring to. This is the FDT response to a heat source here in south of India, and you can see that it does in fact produce a response that has a structure in the northern hemisphere like the Arctic oscillation. And if you take that same source and put it into the GCM, here's the GCM response. And so it is in fact a place to get a big reaction in the Arctic oscillation in the GCM. A related kind of question is one of optimization. Suppose one wants to get a big response to storm track activity over the Atlantic. One can take the storm track response operator, do a little bit of manipulation, then apply SVD analysis to it and find that distribution of heating in the tropics, which gives a biggest response in the Atlantic sector, and this pair is the result that comes out of that SVD analysis. It says if you put a heat source with this distribution in the tropics, you'll expect to get this response in the Atlantic. And this is in fact, according to this analysis, the most efficient way to get a big reaction in the distribution of storms. And we can test that out in the usual way now. What FDT is referring to is this reaction. If you take the response operator and put that right singular vector into it, this is what the response looks like according to the FDT operator. If we put that same distribution into the GCM, here's how the GCM actually responds to it. So you see we are, in fact, getting a big reaction in the storm tracks in the Atlantic. So FDT has given us good information. And the final application I want to mention to you is one of attribution. This is a problem which is very prominent in climate science these days. One is given a particular circulation, and the question is, what is producing that circulation? So it turns out that these response operators could give you information like that. So here's a situation where we've taken the general circulation model and put this heat source in, and here's how the GCM responded to it. Now let's assume we didn't know this. All we knew was how the system reacted. We can operate on that by the inverse of the response operator and pretty much, in fact, retrieve the forcing that was used. So this is a application of the theorem for attribution. Okay, so those are results that I hope help you see the applicability of FDT to the atmosphere, and show you some of the power that is at your disposal once you have generated such response operators. Now I'm going to spend a little time telling you about this particular application that I've been making of it recently. Now I'm going to, I now have trust in the operator, and now I'm going to use it to try to understand something about the sensitivity of the response to how a heat source, properties of a time-varying heat source in the tropics. And as I do this, I'm interested in things like how sensitive is the structure of the response to the propagation speed of the heat source. I'm interested in how the response compares to the more familiar structures and feedbacks that we have become familiar with from the response to steady forcing, and I'm interested in whether some of the basic linear dispersion ideas actually carry over now and can be seen in these responses. Okay, so I think there are two basic methodologies that I've been using to explore this. One of them has to do with this idea that I've been telling you about, how the response to an arbitrary forcing can be thought of as the response to a sequence of pulses. And this is one way that one can explore this. But I think I'm not going to take time to describe this part of the work to you. Instead, I'm going to tell you about the second approach that I've been taking, in which I've actually been putting moving heat sources into the system and seeing how the reaction depends on the rate at which or the speed at which the heat source is moving. So here would be an example of the kind of situation that I'm interested in. I've got this heat source that I insert into the GCM, and I just move it along the equator at a particular rate. And I have to do this for many realizations to see on average how the system is reacting to this heat source. So I want the response that in some sense is independent of the particular distribution of the high frequency variability. So to do that, I'm actually using ensembles of 15,000 members. Now, I just want to point out to you the practical problems. And if this is the means by which you are going to try to study this problem, this would be a very large impediment, right? If every time you wanted to see, if for every heat source that you were interested in, you had to do a 15,000 member ensemble with a GCM, this is a huge undertaking. And the idea is that you can get essentially the same information, maybe even better information, just by using these FDT operators. All right, so anyway, that's my sales pitch. Here's how the GCM reacts when this heat source is moving towards the east at a rate of 8 degrees of longitude per day. So this is like a very fast, this is on the fast end of the spectrum a variability for an MJO. This is kind of a fast-moving heat source in the MJO family. And so here's the upper tropospheric stream function response depending upon where the heat source is as it moves along the equator. And so you can see how the structure is changing somewhat. You can ask questions like, at what position is the heat source when North America first starts to feel its effects, that kind of thing. Here's the corresponding set of solutions as we put this moving heat source in the response operator. So I think you can see that the FDT is capturing most of this sequence. There is one aspect that it doesn't do a very good job at, and that is in this gravest mode of this spherical harmonic, the one that's giving you blue in the northern hemisphere, red in the southern hemisphere, the sine latitude associated or Legendre function. Other than that, FDT is doing a nice job of reproducing this sequence. So, and this is not a surprise. I showed you that it does a good job of reproducing how the system responds to a pulse. So it's not a shock that it's also able to reproduce the response to a moving source.
Quick question.
Yeah.
Small plots, it seems like FDT puts more structure than the GCM has.
Yeah, and a lot of that I think has to do with this one grave mode, which it's not doing very well. So for example, you see this low right here, which looks weak over here, a lot of it is being masked by the fact that this sine function mode is too strong, or it's too weak in FDT. If I took that out of that, you would see that in fact the structures are pretty similar. I'm not saying they're identical, and in some ways I actually trust the FDT more. I had to use 15,000 for a reason. These panels here are starting to converge at 15,000, but these are not. If I had more, even more, the solutions would change somewhat. What I'm trying to say is that these are affected somewhat by sampling. Okay. So, if we do a collection of solutions like this using FDT with the heat source moving at different rates, we can then compare the properties of the responses. So in this figure, I'm showing you the response to 5 heat sources moving at different rates, all the way from very rapidly towards the west to very rapidly towards the east. And what I've plotted is the response as the heat source is at 150 east in all cases. So I think you can see that the response is a very strong function of the rate at which the heat source is moving. And we can also see that the linear theory qualitatively did in fact give us some good guidance. Just as we saw much earlier in the presentation, for heat sources moving towards the west, we have this strong meridional component to the ray path. We see that as it moves towards the east, this Doppler effect is compressing the response. So linear ideas did give us some guidance as to what to expect. But now, using this operator, we've included all these other feedbacks, which that simple linear situation was not taking into account. Okay, now there's one last result here I want to show you, and I hope you'll bear with me. It's going to take me a couple minutes to explain how I've done this. Yeah, but I like the final picture, so I'm going to take a couple minutes to show you how I did this. All right, so here's the situation. We have this sequence of responses for the heat source moving at some particular rate. And we want to be able to summarize this set of responses. So the way that I've chosen to do this today is the following. First, I have taken the heat source at its position at each location on the equator, and I've averaged them together. But before doing the averaging, I have shifted the patterns in such a way that the heat source is at 180 east. And that produces a picture like this. All right, so this is taking out the dependence of the solution on the longitude of the heat source. But you can see that a fair amount of these responses does survive that averaging, because there are certain properties which they have in common, in particular, like the phase relationship between this tropical quadrupole and where the heat source is, the general scale of the response in mid-latitudes, that kind of thing survives this kind of averaging. So I've done this for heat sources moving at different rates along the equator. So here's an example of such an average when the heat source is moving towards the west at 8 degrees per day. This is for steady heat sources. This is for heat sources moving 4 degrees per day towards the east. And so we can see now in these translated averages, we are capturing some of the things that we had seen in the response to specific locations of the heat source, the kind of things I've mentioned several times now, this difference in ray path, difference in the scale of the response. And so now now we have a picture like this for many different propagation rates, and now we want to summarize those pictures. And the way I've done that in this case is to focus on mid-latitudes in this band between these dashed lines, and I've done a latitudinal average. So now I've reduced my two-dimensional picture to a summary of what's happening in mid-latitudes as a one-dimensional picture. In this diagram, I have plotted those one-dimensional results as a function of the velocity or the propagation rate of the heat source. And so this is what I was after. I wanted to know how the response, in this case in mid-latitudes, depends on at the speed at which the tropical heat source is moving. And so you can see that the response is in fact a very strong function of the rate at which the heat source is moving. And FDT has allowed us to construct such a picture. You wouldn't be able to do this using other methodologies. And so the kind of things that I notice are that for sources that are moving towards the west, the phase relationship between this lobe and where the heat source is quite different than for heat sources that are not moving as rapidly towards the west, or which are stationary on into the eastward moving heat sources. Another thing you notice is how the scale of the mid-latitude response is highly dependent on the propagation characteristics of the heat source. The more rapidly the source is moving towards the east, the smaller the scale is. Okay, the last thing I wanted to show you is the same kind of picture, but instead of looking at how the mean circulation is responding, we can also ask how the storm tracks are responding, or in particular how these feedbacks associated with storm track variability are reacting. I told you that one of the fundamental, really interesting properties of how the system reacts to a stationary heat source is that you get this positive feedback with the storm track eddies. So I wondered whether you get the same kind of feedback when the heat source is moving. That is, can the eddies react rapidly enough to still give you this kind of positive feedback if the pattern is moving rapidly? And so that's what this pair of pictures is. Here again is this kind of average picture of how the mid-latitude response of the planetary waves is a function of the propagation rate of the heat source. Here's what the feedback looks like for those same cases. And you can see that the feedback is in fact pretty much following the dependence of the circulation itself. So this positive feedback that we saw, that we've come to understand for this case of stationary heat sources like El Nino, carry over to cases where the source is moving like the MJO. All right, so those are some applications. I'll let you ask me a question about that because guess you will. And So now I just wanted to end, first of all, by giving you the bottom line. The bottom line is, I think based on these results, that FDT has a lot of potential for answering questions that are of interest to climate science, questions like attribution control, optimization. Just as a nice way to explore the system. There are a couple other applications that are not obvious from what I've shown you, but I just wanted to take a minute to point out. First is having to do with model evaluation. I think FDT is telling you a property that your models better have if they're going to react to an external source in the same way that nature does. You better have the same, your model better have the same lag correlation statistics that nature has. So it seems to me this is a natural metric by which to rank models and tell whether your model is better than another model and how similar it's likely to behave to nature. The second thing is that I think this operator is a nice way of capturing certain sensitivities of the system. We heard earlier yesterday about an idea, kind of I think what it amounted to was a kind of a one-dimensional or a univariate counterpart to what I'm talking about. This is a multivariate way of condensing the sensitivity properties of the system in an operator. And the last thing I wanted to do was to be honest and tell you about certain problems with the methodology, problems maybe some of you might want to address someday. One is that it does take a lot of data to construct these operators. Now, but it may be that if we're clever, maybe we won't need to use as much data and still get operators that have some value. So for example, maybe by being clever about the vector that we use to represent the state of the system, maybe we can reduce the data requirements. The other problems having to do with the fact that my impression right now is that the model I've been testing with is perhaps a more linear reaction to an external source than other models do, so that might turn out to be a problem. I was using a perpetual January simulation. There are some ideas about how to have this carry over to a system that has seasonality. Andy Might has worked on that some. I was assuming that the PDF was essentially Gaussian, that there are probably ways to get around that a little bit. The thing that I'm about to work on is to apply this to another, a more complicated system, one in which we include the effect of the ocean. Thank you very much for your attention.
Thank you, Grant. We have a few minutes for questions. Please state your name.
Hugo Lambert, excellent. Thanks. Sorry if I've misunderstood maybe some elements of your talk, but I wondered if there would be any application for this, say if we were crazy enough to want to try to do some geoengineering. Could we start with a kind of desired surface temperature response and then work out where to apply the heater?
Well, I think this is a conclusion one can, yes, the answer to your question is yes.
Would this be a particularly good way of doing it if we had to do it? So?
I think this would give you some guidance. In fact, on the slide that I labeled control, I was tempted to say climate control, but I was afraid that that was a kind of a hot and button way to describe it. But if you're interested in geoengineering, this could give you some guidance as to efficient ways to produce a particular response.
Can I just ask a question about this? Tim Palmer, ECWF from Oxford. The data, well, it's sort of linked to this data requirements question. If you suppose you were only interested, suppose you're forcing projected onto a small number of EOS, maybe one or two, and you're only interested in the response in terms of those leading EOS. I guess you've still got to construct your operator U. And my question is, how, within that kind of construct, how well can you construct that operator from just a few EOS rather than the 1800 that you used? if you're just only interested in the response in terms of the
Right. Yeah, and the answer is not very well. That's not, you can't just ask, it's not enough to have the relationships just for the components whose response you're interested in. You have to have the interactions which lead to that. And so, unfortunately, this is not the answer. We're going to have to be more clever than just narrowing the problem in that way.
The model, sorry, Richard Kleeman, NYU. The model that you're using here is R15, correct?
Yep.
What's the sensitivity to increasing the resolution, do you know?
Sensitivity of what?
Well, of the U operator, for example.
Well, it's not just resolution dependent. It's going to what you're asking is how does the covariance structure of it? You're asking how does the covariance structure of a system depend on the resolution? That's a question that's of interest. You need to know that to know how the FTT operator is going to change, but this is a more general question of how do the lag correlation statistics of a model change when you change the resolution, and there is no simple answer to that question. But I think that's the way to think about it.
Sure.
It all comes down to the lag correlation statistics.
Judith Brunner from NCAR. You took the integral over all lag correlation statistics from 0 to infinity. What do you do in practice? Which lags do you have to include? Where do you
Well, when I'm doing the study problem, I'm actually only taking lags out to about 30. Beyond that, the correlations are so weak that they're really not contributing anything. If you're, but for other problems, well, in all cases, what matters, all you have to do is keep lags for as long as the covariances are non-negligible. So you just don't want to ignore what will turn out to be contributions to the response. Now, I think one way of reducing the data requirement problem is to apply this to shorter timescale problems, and this is something I'm doing right now. You need to do the steady response problem, you need to include lag correlations for as long as the correlations are non-negligible. But if you just want to know how the system's going to respond, say, a week from now to a pulse, then you only need lag correlation statistics over a 1 week lag, okay? And you're in much better shape to try to estimate those than you are to try to estimate the weaker 20-day lag correlation statistics. So part of the answer to your question is it depends on the problem you're applying it to. If you just want to know how the system's going to respond 5 days from now, all you need are lag 5.
Off in the back.
Yeah, so Peter Haynes, Cambridge. I guess picking up that last point you made about, you in your talk you were looking quite a bit at the transient response, the shortish time response. But I mean, one question is, I mean, how relevant is that in practice, right? Because you're looking at an ensemble average,
Right.
short time response, right? I mean, you're not.
Yes,
You
but
certainly never observe that in the real atmosphere, can you? Right? I mean, that's,
But we are actually looking at the response. The problem in the atmosphere is that there are, superimposed on that is a lot of other variability. So I agree that for any individual, this is different from any individual realization, but this is the forced response that we're looking at, in the sense of, I mean, the definition of the forced response in such a system is the ensemble average.
yeah, exactly. But my question is it any use?
Well, I think it's telling you, for example, I mean, the one way I like to look about this is this fact that I was pointing out. One thing this tells you is how close does the heat source have to be to a given location in the exotropics for it to have an effect. I think this is telling you something about which parts of the domain can have an effect on where you live, for example. So this is one practical application.
Yeah, I'm sort of questioning. I'm purely questioning this sort of short time
Yep.
aspect. Because if you're looking at the steady response, then you've got the idea of time averaging
Yep.
being semi-equivalent to ensemble averaging. Right? So there's a sense in which you might observe a long time response.
Right.
Isn't it?
Right.
And I guess another question is, I mean, Tim asked the point. I thought he was going to ask about could you truncate the system, right? Then it seemed as though he didn't quite ask that. He asked, supposing you're only forcing in one or two EOFs.
No, I thought you wanted to know, suppose all you want is the response of the NAO. Isn't that your question?
Yeah.
Yeah. Can you get away with a state vector that only has the NAO in it, or
So
the NAO plus the way you want to force? Of course, you have to include functions that can represent the forcing. So this is another.
I mean, my question was, if you calculated your U operator from just the NAO,
Yeah.
how well would that approximate
Right. Yeah.
thing? And you're saying it doesn't.
It doesn't. Yeah.
But a kind of generalization of that question is, could you get away with, say, 20 or 40 EOFs? Working a basis of 20 or 40 EOFs,
Right.
say, rather than 1800 or whatever it is.
I think this is only something that this is part of my call for looking into these questions. I don't have the answer to your question. This is the kind of thing one would want to investigate to see if there's some way to intelligently reduce the dimensionality.
Could I just ask Tim Palmer again one last quick question? Have you ever thought about, and would this be a useful thing to do, take the systematic error of the CCM and invert it with the U operator? Would that tell the model development people anything useful about the source of the model biases?
I think so. I have. Yeah. The answer is yes. And as is often the case with these things, what it's going to tell you is what sort of a missing forcing, but it's going to take some physical reasoning then to decide which parameterization is at fault. Something you might get lucky and the signature might scream a particular aspect of the system, but other forcings that you get, it could be many possibilities, and so it's of some use, but it's not a silver bullet. It has not been done yet.
Okay. So let's thank Grant again for first making thoughts.